dinitrogen tetroxide. I have a delta G value. I need to know what direction the reaction will proceed if I have a mixture that contains a partial pressure of 0.25 atmospheres of nitrogen dioxide and a partial pressure of dinitrogen tetroxide of 0.6 atmospheres. Okay, I'm asking what direction will the reaction go. Now, if I had a big K value, I just compute Q and I'm done. But I don't have a big K value. Okay? Since I don't have a big K value, I'm going to have to use Gibbs free energy in order to predict this. All right? So, this problem, even though it doesn't look like it, is asking me to calculate delta G. Well, the formula for delta G, I have the standard Gibbs free energy plus RT log of Q. Luckily, the problem gave me delta G 0. Okay, I'm going to go ahead and, well, we'll leave this as kilojoules. Minus 5.40 kilojoules per mole per Kelvin, plus R is going to be 8.314 joule per mole per Kelvin. The temperature, I'm not told the temperature. I'm given delta G at 298, so I'm going to assume my temperature is 298 Kelvin. And then log of Q. Well, Q, I'm dealing with pressure, so this is going to technically be QP. I have the partial pressure of dinitrogen tetroxide divided by the partial pressure of nitrogen dioxide squared. 0.60 divided by 0.25 quantity squared. Did I actually calculate that? No, I did not. 0.25 is going to be 25 squared is 625. So it's going to be 0.0625. So I'm going to have something on the order of something a little bit less than 10. What do I get when you plug that in? 0.6? 9.6. Okay, so I have a natural log of 9.6. Okay. So, I have 5.40 times 10 to the third joules. I'm going to go ahead and get rid of the kilo per mole per Kelvin, plus, this log is greater than 1, so I know it's positive. I'm going to get 5.609. What did I do here? Okay. 5.609 times 10 to the third joules per mole, and that's wrong. I'm sorry. That's not joule per mole per Kelvin. That's not joule per mole per Kelvin. I'm the one who harps on units all the time, and I screw units up. I need more sleep over there. Joule per mole. I add those two quantities together, and I'm going to get a positive 208 joules per mole. Since delta G is greater than 0, which direction does my equilibrium shift? Towards reactants or towards products? Or am I at equilibrium? Okay. 0 means I'm at equilibrium. I'm not at equilibrium. Since delta G is positive, I'm going to shift towards reactants. Okay. Going to shift towards reactants. All right. Now, if there's a relationship between delta G0, and Q, we hope, hopefully, there's a relationship between delta G0 and K. And there is. All right, here it is. Well, here's the equation we already have. Those of you that have seen me, that have me in lab, you already know where I'm going from here, because this is what I did during the workshop. All right. So I'm going to use this relationship between delta G and delta G0 and Q. At equilibrium, the definition of delta G is that delta G is equal to 0. By definition, at equilibrium, Q is equal to K. So I'm going to make those substitutions. All right, of course, we'll use K and Kp for gases and solutions. So I'm going to make those substitutions. 0 is equal to delta G0 plus RT log of K. Solve that for delta G0, and I get minus RT log of K. It's blue, it's important, memory bank it. All right. So let's look at this for a second. If we have a very large value of K, what does a very large value of K tell us? We're product favored. Okay, if I have a very large K and I take the natural logarithm of it, I have a positive quantity. Right? Temperature has to be positive. R is positive. So delta G0 is going to be negative. All right. Now, if K is approximately equal to 1, really I need to know the stoichiometry before I can actually say whether I'm product or reactant favored, but I'm close to the same. I don't really favor products over reactants too strongly. All right. Natural log of 1 is 0. What that tells me is that delta G0 is going to be 0 for a reaction that neither favors products nor reactants. And then the last possibility is if K is less than 1, that would be something like a weak acid. I favor the reactant side of things. If K is less than 1, the natural log of a number that's less than 1 is going to be negative. Since it's negative, delta G is going to be positive. Delta G0 is going to be positive. Right? So delta G0 tells me the magnitude of my equilibrium constant. Whereas delta G itself tells me which direction I go to achieve equilibrium. They're telling you two different things. And they look remarkably alike, unfortunately. You'd think they would come up with different symbols for them. You'd think. All right. So we can extend this also to other temperatures. And delta G0 as a function of temperature is equal to minus RT times the natural log of the equilibrium constant at the T temperature. All right. So if I know the equilibrium constant as a function of temperature, then I also know delta G0 as a function of temperature. Okay? All right. Laughing gas. Some of you might have needed that last night. Laughing gas decomposes according to the following. 2 moles of dinitrogen oxide decompose to give me 2 moles of nitrogen and 1 mole of oxygen. Delta H at 298 is equal to minus 163 kilojoules per mole. Delta S0 at 298 is equal to 148 joules per mole per Kelvin. All right, so there's the problem statement. Question, what is Kp at 25 degrees C? Okay. Well, we're looking for K. The only equation that we have that relates K to thermodynamics is the following. Standard Gibbs free energy of the reaction is equal to minus RT natural log of big K. All right. Well, we're not given delta G0 for the reaction. We're going to have to calculate it. Luckily, we're given enough information to calculate it. We're also asked for K at 25 degrees C. All right. So delta G0 for the reaction is also equal to delta H for the reaction minus T delta S for the reaction. Well, I'm given delta H and delta S, so now it's just plug and chug. So, delta H is minus 163 kilojoules per mole. Minus my temperature is 25 degrees C. And let's just cheat and use 298 Kelvin. And then my delta S is 148 joules per mole. This is going to be minus 163. I'm going to go ahead and leave it in kilojoules per mole. Minus 298 times 148. That's like 300 times 300 times 150. It's going to be really, really big. This is going to be minus 44.104 kilojoules per mole. Tells me that my delta G is going to be minus 207.10 kilojoules per mole. Now, that tells me delta G0 for the reaction. I need to calculate K at 25 degrees C. So, I need to solve this for K. Delta G0 for the reaction is equal to minus RT log of K. Solving this for K, I'm going to divide both sides by minus RT. This is going to be equal to the natural log of K. To get rid of the natural log of K, I exponentiate both sides. So I have e to the minus delta G over RT is equal to K. So now it's plug and chug. E to the minus 207.10 kilojoules, but I have a minus sign in front, so it's going to be positive 207.10. My units on R are joules. So what I'm going to do is I'm going to go ahead and convert this from kilojoules per mole to joules per mole. And now I need to divide the whole thing by R. 8.314 joule per mole per Kelvin times my temperature, which is 298 Kelvin. My Kelvins cancel. My joules per mole also cancels. So I'm going to have E to the positive 83.59, and it is a dimensionless quantity, no units. It's all equal to K. So K at 298, or 25 degrees C, is equal to 2 times 10 to the 36th power. That's huge, yes. In the exponent?
No, in this expression.
Which one? This one? Because I left that Kelvin off. Sorry, got ahead of myself. This is entropy. Entropy always has units are always energy per mole per Kelvin. All right. Okay, so that gives me a really, really large K. K is extremely big, meaning does this favor reactants or products? Products. Okay. Now we would expect that by the fact that this is a relatively large negative G, delta G0. All right. We can do that again. Calculate K at now a 40 degrees C. Now, my delta H and my delta S, I'm going to assume are temperature independent. But my delta G0 is not. I have to recompute delta G0 because I'm at a different temperature. So, delta G0 for my reaction at 40 degrees C is still equal to delta H for the reaction minus T delta S for the reaction, but my T changes. Okay, so this is going to be minus 163 kilojoules per mole minus 40 degrees C, 40 plus 273 is 313 Kelvin. And then my entropy does not change. It is a positive 148 joule per mole per Kelvin. My Kelvins will cancel this time without any special work. And without filling in all the gas, I'm just going to tell you what the delta G is here. It's minus 209.32 kilojoules per mole. Okay? I go from 207 to 209. Is this thing going to favor, am I going to, as I increase temperature, am I going to shift towards products or reactants? Products. Okay, we know that just simply from the size of delta G0. Let me ask you another question. According to Le Chatelier's principle, if delta H is negative, where does energy go? Products or reactants? Delta H is negative, that means the system is losing energy in the form of heat. That means energy is effectively going to be a product. So if I increase the temperature, that doesn't work. Why doesn't that work? Delta H is negative. The system is losing energy, meaning the system is exothermic, meaning the energy is going to be a product. Why does temperature goes up? There's a problem now. I know where the problem lies. We've never taken into consideration entropy. Okay? I'm going from 2 moles of gas to 3 moles of gas. Okay? Because entropy is here, what that tells me is that my little rule that I have for adding energy to reactants or products works in most cases, particularly in solution. But it doesn't necessarily work if I'm talking about a gas phase reaction, because I have to take into consideration entropy. If I had the same number of moles of gas on both sides, my entropy would be much, much smaller. Meaning that I could use that argument. I can't here because this is going to be an entropically driven reaction. Let's go ahead and calculate big K. I'm going to plug into the exact same expression over there. I'm going to have K is equal to E to the minus delta G0 of the reaction divided by R times T. So we're going to have E to the positive 209.32 times 10 to the third joules per mole. Divide that by 8.314 joule per mole per Kelvin times by 313 Kelvin. I'm going to get E to the 80.4. So my big K at 40 degrees C is going to be 8.6 times 10 to the 34th power. Is that right? I didn't bring a calculator with me. Who has a calculator? Something wrong up here. Seriously wrong. If you find it, shut it out.
decimal.
He'll cut it before.
He told me to just change one. To just change it to check your cut one. He wanted an example like no percentage, no percentage.
Okay. Not a problem with the math. K's right. Okay. There's something buggy going on here.
Why is it e to the negative delta? Why is it?
The reason why it's minus delta G is because my formula here, when I set this equal to 0, I have minus delta G over RT is equal to natural log of K, and I have e to the minus delta G over RT. So I changed the sign, all right? This is a bigger quantity, meaning this should be bigger than that, and there's something weird going on here. Second delta G is wrong. What's
Yes,
this?
just for the second equation. If you do the,
That's wrong.
Get the value you put down is wrong.
The value I put down is wrong.
Yes, you know about that.
What is it supposed to be?
464.87.
454,
464.
464.
Wait, I lied.
What do we get? Minus 163,000, 160, minus 163,000, minus 313 times 148. What do we get? What I had before was right. Your grade just changed. Okay, so what I had before was right. This is supposed to be 209.32. Okay. Delta G is becoming more negative, meaning I should, if delta G is becoming more negative, I should favor products more, right? Okay? Delta G is going from 207 to 209. It's not changing much, but it is changing. It should be becoming more product favored, meaning my K should be getting larger, but it's not. Why? Because I have a bigger number here divided by the bigger number here. Because the temperature is changing. Okay. All right. Regardless, you know how to calculate K. The math is right. There's something funky about this problem, and I'm going to figure that out before I fix the slide again. Otherwise, I'm going to look like an idiot. Okay. So, plug the numbers in, and you can calculate K. This gives us a way of calculating K for processes where K is either really, really, really big or really, really small. All right, all you need to know is the thermodynamics so you can calculate big and small Ks, and you don't necessarily need to do the experiment. All right. So delta G0 is a constant for a specific reaction at a specific temperature. Tells me basically the same information as K. Change T, change K, I'm going to change delta G0 like what you just saw. Delta G gives me the same information as Q versus K. In other words, it tells me the direction in which my equilibrium shifts. So delta G will change as the reaction goes forward. It goes to 0 at equilibrium. So that gives rise to what we call a free energy diagram. Right. It shows how the free energy, in other words, the Gibbs free energy, changes versus reaction coordinate. Right. This figure is in your textbook, so if you can't read it, I apologize. It's as big as I could make it on this slide. I have delta G0 for my reactants. I have delta G0 for my products on the opposite sides of my extended reaction coordinate. I can calculate the delta G0 for the reactants by just simply subbing over all the delta G0s for my reacting species. And I can do the same for the products. And then I take the difference between the final state and the initial state, and I can calculate delta G0 for the reaction, and that tells me the height difference I have here. Now, the actual shape of the curve, it's complicated. All right, they just simply drew straight lines and made it look nice by connecting the two straight lines with a pretty looking quadratic curve. Is it quadratic? No. All right. Does it really matter for you guys what the shape of the curve is? No. What happens with a reaction is, no matter where my reaction is in terms of coordinate, in the reaction coordinate space, I find the reaction, the extent of the reaction someplace on the curve. If I start at all reactants, my reaction is going to proceed until I reach the bottom of the curve. Just like a marble rolling downhill. I'm going to reach the bottom, I'm going to reach the point where I have the minimum potential energy. In this case, the potential energy is the free energy for my reaction to do work, which is the Gibbs free energy. Okay? Now I'm looking at delta G0 here. I'm not looking at delta G itself. Delta G is in fact the slope of this curve as it goes back and forth. All right? Delta G0 is just the difference in Gibbs energy of the products and the reactant states. All right? Whereas delta G itself is the slope of the Gibbs energy plot, slope of the free energy diagram. All right? So depending upon the sign of delta G0 for the reaction, either I have more free energy to do work in the reactants or the products, or here I have more in the products than I do the reactants, and it changes the sign of delta G. Okay? Delta G0 tells me relatively where the extended reaction is going to reach equilibrium. Delta G is negative, it's going to be towards products. If delta G is positive, it's going to be towards reactants. All right. Regardless, on either one of these things, if I'm someplace over on this area of the graph, I will still proceed towards equilibrium by going towards products, because on both of these graphs, 0 is, well, to the left of where I'm pointing at now. All right? So we get delta G0 from tables. Changes with temperature. The lowest point is going to give me the equilibrium. All right? Delta G is the slope. Approach equilibrium from either side. It depends on Q versus K. We already know how it depends on Q versus K. All right? We've already seen that. Nothing new here. All it tells us, all we now do is we have a relationship between Q and K and delta G. All right? Delta G itself tells us the direction the reaction has to go to proceed to reach equilibrium. Delta G0 tells us the position. Bigger the magnitude of delta G0, the equilibrium lies farther either towards the reactant or toward products. I'm going to figure out what the mistake is here, and I'll get back to you on Friday. Thank you for your time and your attention. I will be posting the next chapter of the lecture notes sometime between now and Friday. Thanks.
I'll upload it.